Hi guys, welcome back to junkminds.com. We'll now get started with binary search algorithm. Binary search algorithm is a searching algorithm that uses a divide and conquer strategy for searching any given data. Now over here, suppose we have this set of data available to us and I'm required to search this value 28 in that particular sequence. Now please observe this, that this data is already in a sorted form. Now, for binary search to work, the data has to be sorted. You cannot apply binary search to the data that has been stored in a random fashion. So, how exactly does binary search work? Binary search, the entire strategy depends on the three variables, the 3 pointers that we create, namely low, high, and mid. Let us get started. So, this is the data. There are 8 values in all. They have been stored in an array which have been numbered, or you can say the indexes exist from 0 to 7, and I'm interested in searching this value 28 in this array. Now to get started, in step 1, what I'll do is I'll initialize this variable low to 0, which is always the first index of this array. High will always be the last index. So if there are say n values in an array, high will always be initialized to n minus 1. X is the value that I'm looking for in this array. The first thing that I do is I'll calculate the mid of this entire range that I have, which is low plus high def 2. So 0 plus 7 def 2. 7 def 2, the quotient is 3. So what I get is I get the first value of mid, which is at index 3. Now the strategy here is I'm trying to locate the value at mid. Now the value that I'm searching is 28. I'll first check if the value that I'm looking for, is it present on mid? If at all I had got the value over here, that was the end of the algorithm. But suppose if that hasn't happened, then I need to just figure out that the new value that I need to search, should I search it just to the left of this mid, or should I go to the right of the mid? So in our example, the value at index 3 at mid is 34, which obviously is not equal to the value that I'm looking for. So how do I proceed? So what I now understand is that I did not find mid, but what I also find is that the value that I'm looking for is less than the value at mid. So what I understand is that if at all the value that I'm looking for, if it is present, it will be present to the left of mid. Please, I still don't know the exact position where 28 would be found, but if at all it's there, it will come before mid. So what I understand is in the next step, I need to just check the left half of mid. I don't need to bother about all these values. So what I do is, now that I've understood that the data has to be searched, I will search to the left of mid. I will now reset my high pointer, because please remember the interval is low and high. The low and high pointer set the interval between which you will be searching the data. So what I'm now planning to do is I'll take this pointer high and I'll get and set it out here. Now what is this position? This is mid minus 1. Please remember, this doesn't change. Every time it will be mid minus 1 if you have to search the interval which is to the left of mid. So the new value of high that I get is 2. So now when I go to my next step, before I start evaluating, this is high and this is low. At any given point of time, low and high will always refer to the indexes. They do not refer to the value as such. Now what this has done is all the values to the right. Now I'm not searching over here, so there are no redundant comparisons happening in the region where I may not find the value at all. Now the process continues. Low is 0, high is 2. I'll calculate mid again. 2 def 2, the quotient is 1. Now again I'll check at index 1. What I find is that the value that I'm getting is 12, which is not the same as 28, the value that I'm looking for. But now what I find is that the value at mid is actually less than the value that we are looking for. So what this means is, if at all the value that I'm looking for is there in the sequence, it would be present to the right of this value. So what I now do is, I want to search the interval only to the right of mid. So I shift my low pointer to mid plus 1. So what happens now? Now this is where I get low, this is where I get high. I repeat the same process. Low is 2, high is 2. I calculate mid as 2 plus 2 def 2, which I get 2. So what I'm finding is the value of mid that I'm getting is 2. So low, high and mid are all referring to this value 2. So now when I compare the value at index 2, it is the value that I found, that I've been looking for. So the match is found. The algorithm returns that value and then it stops. But what if the value that I was looking for is not present in this sequence at all? So where do I stop, or how do I stop? Now please understand this, assuming that I was looking for a value which was say not very, say any other value which is not present in the sequence. Now after this step, what happens is, see, either low gets incremented or high gets decremented. In both the scenarios, what happens is the low and high pointers will cross. Now moment low and high cross, what it means is that I have searched the entire data and the value is not present, and then I can conclude that the value is not found. So over here, what we observe is that binary search will eliminate all redundant comparisons and try and return you the value in the least number of comparisons possible. So that is what is the strategy that we use in the binary search algorithm. So going further now, the efficiency calculations for binary search algorithm. So we now need to come up with the O notation for binary search, and let us try and figure out how can we represent the behavior. Just to recollect, the O notations or the asymptotic notations are basically the representation of the behavior of the algorithm. In simpler terms, if I look at the O notation for any algorithm, I should be able to comment on how efficient the algorithm will turn out to be. Let's first get started with the best case efficiency. Now, what is the possible scenario where you get the best case efficiency of binary search? Now, suppose the value that I'm searching for is exactly in the middle of this interval. So what happens is, I calculate low, I calculate high, I calculate mid, and the first value of mid itself gives me the value that I'm looking for. Now, in such case, whatever be the size of the interval, I'm getting my answer in just one step. So what this means is, I need just one step, or I need just one evaluation to get my final answer. Now whether your array has 10 values or 10,000 values, I'll need just one calculation of low plus high def2 to generate my result. So this is now a constant function, and we know how constant functions are represented, which is order of 1. So the best case efficiency of binary search is order of 1. Now, how about the worst case efficiency? Now, for representing the worst case efficiency, this is going to be a bit trivial, but then this is something which will hold true for most algorithms which follow a similar strategy. I'll elaborate what exactly do I mean as I proceed, but let's try and come up with some method of representing the worst case efficiency of the algorithm. Now, please understand, when will binary search represent a worst case efficiency? Binary search will start searching for a particular value, and after it has searched the entire data and we find that the value that we are looking for is not present, then binary search will generate its worst case efficiency. Now over here, for representing this, I'm going to go with a little assumption. Now suppose I have an initial list of length, say 1024. I have 1024 values for evaluation, and I'm going to make my conclusions based on this. Now you could have taken any value, but it's always better that you start with some power of 2, because you will see when I want to represent the behavior, I want to say that the length of the interval gets halved in each step. So if I take some power of 2, it's always easy. Also, for any logarithmic representations, any power of 2, and precisely if it is 10, it's always easier for us to represent. So 1024, like you all know, it is 2 raised to 10 or 2 to the power of 10. So that is what is going to help me. So now if I want to represent the behavior, how does it happen? Now suppose to start with, I have 1024 values in the interval. After the first step, when the interval gets halved, I'll have 512 values to process. Then this interval gets halved in the next step, then half, and so on. So what we find is, over here, I will need about 10 steps till I reach a stage where there'll be only one value left in this particular sequence. And after that, I'll be able to conclude that the value has not been found. So I want to represent this behavior in mathematical terms. Any such behavior where we see the interval is getting halved or the interval is getting doubled, interval is getting halved or the interval is getting doubled, then we represent it in terms of logarithmic details. So over here, what we find is that this behavior can be represented in terms of log n to the base 2, where if you see that c is the number of comparisons needed and n is the number of values. So if I want to represent the behavior of this algorithm, it is represented as order of log n to the base 2. Now look at the larger picture. When you say order of log n to the base 2, I'm not just talking about binary search. Any algorithm which keeps on working in this fashion, that whatever the value that you give, after every step the length of the interval goes to half, or in each step the length of the interval doubles. In all such algorithms, the number of steps needed, the amount of work to be done, will remain the same. So for any algorithm where the interval goes to half in each step, you will have its efficiency calculations at order of log n to the base 2. So the best case efficiency of binary search is order of 1, and the average or the worst case efficiency is order of log n to the base 2. So that was binary search. We will be going to the program for binary search in our next video. If you wish, you can continue with that right away. Thank you for studying with junkminds.com. I'll see you in my next video with the program for binary search. Thank you. Let's get started with the program on binary search. I hope all of you have understood the example properly. If you have understood the example, the program is going to be pretty straightforward for you. Now here is your C language implementation of binary search algorithm. Now over here, if you see, I've started by creating an array. I'm going to make use of this variable found. I've initialized this variable found to 0. The idea of keeping this found 0 is whenever I'm going in search of a particular value, it may or may not be present in the given sequence. So I've kept this variable found as 0. What I'm planning to do is, as and when I get the value that I'm looking for, I'll change the value of found to 1. So at the end of the program, the value of found will act as an indicator to help me try and understand whether the value has been found or not. Apart from this, what we discussed in the example, I have my variables low, high and mid. Variable index is going to record the index where I found the value that I'm looking for. Okay, so we've started by asking the user about the number of values. We've got n. We've written a for loop which is going to read the value. Now if we go by this particular array, it is like we've written this for loop which has read this array. Now your implementation of binary search starts here. Whenever we start with binary search, we always try and implement low to the lowest possible index and high to the highest possible index. Now in this case, the lowest value of the lowest value is 0 and the highest value is 7. So we've started by initializing low to 0 and high to n-1. If there are n values, the last index is bound to be n-1. Like if you see in this example over here, if there are 8 values, the last index is going to be 7. Then I've asked the user for the value to be searched. Suppose the value given to me is say x. Now please understand this. I've started with this low pointer like this. It will keep moving towards this way if needed, and high will keep moving towards this if needed. Now low as of now is 0, high as of now is 7. The value of low at any given point of time would be less than or maximum equal to 7. At any given point of time, if low and high, they cross each other, in that case, the value of low becomes greater than high. That means you finished evaluating the entire expression. That is why my condition, while low is less than equal to high, till I have not exhausted the entire sequence, what do? I calculate mid as low plus high div 2. Now in our example, if low is 0, if high is 7, 0 plus 7, 7 div 2, the quotient comes out to be 3. So we've placed this mid at 3 here. Now we'll check if the value at a mid is the value that we are looking for. If this condition becomes true, I'll change found as 1 to indicate that the value has been found. Whatever is the value of mid, that is the index where I found the value, I will record this in this variable index, and break, as you all know, will always terminate the loop that contains it. But suppose if this condition is false, means we've not yet found the value that we are looking for, then what do? We will check if the value that I'm looking for is less than the value at mid. If the value is less than mid, now please look at this. If the value that I'm looking for is say less than the value at mid, then I need to check the value to the left of mid. So what I need to do is I'll change this high and get it to mid -1. this is going to become the new high, and that is exactly what I've done over here. If x is less than a of mid, high is mid minus 1. If this condition is false, means that the value that I'm looking for is greater than the value at mid. So in that case, I'll shift low is equal to mid plus 1. Now this while loop will keep checking the value if the value is found at any given point of time. If the value is found, this condition would be true and my program terminates over here. Now once this while loop terminates, I'll just come out and I'll check if the value found is 1. That means that the value was found. If this continues to be 0, remember I had initialized found as 0 right in the beginning. If the value of found never gets changed here, means the value was never found, then found remains 0. This condition will become false and we'll say that the value is not found. Hence, this is how you will be able to implement the binary search algorithm.